In this video, we are going to see electrophilic aliphatic substitution and one of its mechanism, that is SE1 mechanism. This SE1 mechanism is analogous to SN1 mechanism of aliphatic nucleophilic substitution reaction. Okay, so we know that SN1 mechanism have two steps. First is slow ionization of the substrate to form a carbocation and a leaving group. Then the second step is the fast recombination of this newly formed carbocation and the attacking reagent. Similarly, in case of SE1 mechanism also have two steps. First step is step 1, that is slow ionization step. That is our Rx will cleave to form R minus and X plus. So, in case of SN1 mechanism, we have R plus instead of this R minus carbanion. Okay. Then the second step is fast step. That is fast recombination. This R minus will combine with our electrophile to form Ry. Okay, this is slow step. This is fast step. We know that the slowest step is the rate determining step. Since in this rate determining step only one reactant is there, so that it depends upon the concentration of the substrate only, and the reaction will be unimolecular. In many reaction, in many electrophilic substitution reaction of aliphatic compound, there is evidence for unimolecular mechanism, so that this mechanism may be operating. So, about the stereochemistry. In case of SN1 mechanism, we have a planar carbo intermediate is formed. That is, planar carbocation is formed. If you write the structure like this, here C, then one R group is we label as R1, then another R group R2. Okay. So in case of SN1, our intermediate is planar, so that the nucleophile can attack from both sides. That is, the attack from both sides are equally probable, and the product will be racemic mixture if these three groups are different. But in case of carbanion, there is instead of having a planar structure, there is a pyramidal structure also. That is, in case of planar structure, the carbanion carbon will be in sp3 hybridized. In case sp2 in case of planar, sp2 hybridized, and in case of pyramidal structure, the hybridization will be sp3. Okay. So, in case of nucleophilic substitution reaction, or if there is a planar carbanion, instead of here positive charge, we can write it as negative charge, and instead of nucleophile, we are adding this Y plus. Okay, so this can attack from both sides. Such conditions are observed when there is resonance stabilization of this carbanion. Okay. So both the product are equally possible, that is racemic product will be observed. In case of pyramidal structure, the condition will be different. That is, we are writing like this. Here this is the leaving group, then R1, R2. Okay, after leaving this leaving group, Sx plus, leaving its electron here, this electron is situating in this sp2 hybridized orbital, so that if this carbanion is holding its structure as like this, then the incoming Y plus will attack over here, and we have retention of product. So if but even though if it have a pyramidal structure, pyramidal carbanion is formed, there is chance of pyramidal inversion as in case of amines. That is, this lone pair will come here, and this R1, R2, R3 will go here, and that is there is exchange of these two structures, so that the relative position of structures of R1, R2, R will be different in these two structures, so that due to pyramidal inversion also racemic product can observe. But in case of this reaction, stereochemistry cannot be predicted as very easy. It depends on many factors like effect of solvent, etc. So let us have an example. Let us see this example, that is alkoxide cleavage reaction. Here this is an alkoxide. This is a resonantly stabilized R group is the like PH, C, C2H5, CH3, etc. This R can be groups like this kind of group. That is here this negative charge on this R may stabilized with this phenyl ring also. Okay. So so that the ring will be, the carbanion will be planar. Okay. In such cases also, by varying the solvent, the product RH can range from 99% retention to about 60% inversion, including complete racemization. So let us have a discussion on why this happens. First of all, in case of solvents with low polarities like benzenes, etc. Here this is a protic solvent, not protic solvent. It have a hydrogen, but it can interact with this hydrogen, can interact with this negative charge. That is R, C, R2. Then this this hydrogen from the solvent, or alkoxide O minus. This is O minus. Then this O minus can interact with the hydrogen of the solvent. This is solvent can be represented like this. But the peculiarity of this kind of solvent is that here the BH bond is not polar, so that it have a hydrogen bond like that much strong bonding, or this solvent is have a low dielectric constant, so that this this ion is existing as ion pair, intimate ion pair. That is the counter ion of this molecule will be here. So the structure, the interaction will be like this. Due to the interaction between this, that is this negative charge is solvated by the hydrogen of this solvent, so that it is very easy to interact from same side to this R, so that RH is formed. Okay, so in such cases the product will be like this. Here first of all this bond come here, and this will go here to form a carbanion, and this carbanion is solvated from here, so that since this solvent is already present near here, near this side, so that it is easily solvated, and this hydrogen from solvent is going here, and we have first of all the intermediate will be R minus, then the next product will be C double bond O R2, then there will be interaction between this solvent and the hydrogen of the hydrogen of the solvent and this R group, and then finally this RH is formed with the retention of configuration, and the remaining product will be B minus and CO R2. Okay. So this is the case when we are taking solvents like benzene which have a low dielectric constant. That is, in case of low dielectric constant, there will be the ion exists as ion pair. Okay. Then the next condition is in presence of polar protic solvent or protic solvent. In case of protic solvent, what happens is, here we write like this, R2 double bond O. So in case of protic solvent, this anion is stabilized by the solvation of the solvent. Okay, so there will be also, but here the problem is, here this polar protic solvent have usually high dielectric constant, so that it exists as a solvent separated ion pair, so that the counter ion will be separated like this, here M plus. Okay, so the interaction is like this. So after, sorry, here not double bond, here after forming a double bond, that is after formation of this carbanion, the remaining portion of the leaving group will solvate the molecule, so that the product will be like this. Here R minus is solvated by the remaining portion of this R2, so that this portion will not be free, so that another solvent molecule can interact only from backside. So BH interact only from backside, so that a new HR bond is formed. Okay, since this solvent is interacting from backside, the product will be inverted product. Here retention, here inversion. In case of polar aprotic solvent, that have there is no hydrogen in that, active hydrogen in that. In such cases, here the carbanion formed will have a recently high stability, so that inversion can happen. Pyramidal inversion can also happen, so that both product will result, that result in retention of configuration. So in case of this solvent have with a dielectric constant, low dielectric constant, which have a hydrogen, have a retention of configuration, then polar protic solvent will have inversion of configuration of this, in this case that is alkoxide cleavage reactions. Then in case of polar aprotic solvents, there will be racemic mixture.